In order to do a recent lab report, I observed a ping pong ball drop from rest and fall somewhat slowly, as in slower than a rock, but straight down. The purpose of doing this was to observe the gravitational pull and the turbulent drag force on the falling object, which I analyzed through observations and computational models. The basis of this was Newton's second law of motion, which is V final is equal to V initial plus F net over m multiplied by delta t. Also used was the equation for weight force, which states that the weight is equal to mass multiplied by g, which is in this case 9.8 meters per second, or the gravitational pull of the Earth, multiplied by negative j hat, or the direction of the ball, which is negative in the y direction. Also used was the equation for turbulent drag force, which states that the drag force is equal to negative b multiplied by the velocity squared. Here is the analyzed video, shown in tracker. As you can see, the ball falls straight down, with the ball accelerating and going closer to terminal velocity, as shown here. The speed is 30 frames per second, as shown here. The calibration stick shows the diameter of the ping pong ball, right here, which states that it is 40 millimeters long, and the axes are slightly tilted in order to compensate for minor camera tilts. As you can see, the ball travels in the negative y direction. So here is the code of the two computational models. The one on the left shows only gravity, and the one on the right shows gravity and turbulent drag. In both, the ball's mass is 0.0027 kilograms, with the ball's position, the initial velocity, and the starting time all at 0. As we move down, we see that since the video is less than a second long, 0.001 seconds seems to be appropriate for delta t. The magnitude for the weight force, g, is equal to 9.8, and the y-axis unit vector, shown here, is 0, 1, 0. The calculation loop continues until 0.601 seconds. Both models, this one and this one, show an equation for the weight force, shown here, as well as an equation for Newton's second law, and two equations that each predict the the position and the time, respectively. These are the similarities between the two computational models. So here is your computational model. Now, as you can see here, there's an extra formula in this model. The formula for turbulent drag force, which is the drag force is equal to negative b multiplied by velocity squared. Since there is a new value that is acting on the item, in this case ping pong ball, I add the drag force to the weight force to calculate the net force. Now, if we don't assign a value to b, then b just remains 0. But we have to assign a value to b. Because if we don't assign a value to b, then just 0 multiplied by any number is just equal to 0. Which will make the drag force 0, and as far as we know, the drag force is not 0. So I did a little guessing check, looking for a b that would cause for the final position in the computational model to match the observed. Doing so, I inferred that b is equal to 0.0001. Very small, but it's still something. I also added arrows that begin at the ball's initial position, as shown here, and extend for the weight or drag force multiplied by an appropriate arrow scale, which I showed to be 76. And now here's your computational model. So we have taken all the data and put it into a spreadsheet. On this column, we have the time. In column D, we have the experiment position, which is shown in this chart with the blue line, as you can see here. And in column F, we have the model position with gravity, which is shown by the red line in this graph. And we also have model position with gravity and drag, which is shown by the yellow line in this graph. Now, when you see this graph, you can infer that all of our predictions were accurate. Now, when we zoom in, we notice that beside that the red line begins to appear here, what we begin to notice is that there is a minor gap between the model position with the gravity and drag and the experiment position. One possible reason for this might be the code. If you remember, in the code, we made a rough estimate for b when we were creating the equation. Here it is. As you can see, b was just an approximation. So with an approximation, it is highly unlikely that you will actually get something that will exactly match the experiment position. Another thing worth noticing is that none of these graphs show a terminal velocity. Probably because that the drag force isn't strong enough. This is the Model 4 drag force, but even with the drag force programmed into it, you see there is no arrow, no blue arrow here. This means that the drag force is very low, so therefore it is not a surprise it hasn't reached terminal velocity as of right now. Maybe if the drop lasted longer than 0.6 seconds, as 0.66 seconds is like barely anything. Or maybe if the height of the ball, when it was first released, was significantly higher, then we would have seen some signs of terminal velocity. Well, now what happens if the ball is thrown down? Well, in order to represent this, I've created the initial velocity equal to the vector 0, negative 15, 0. So as you can see here, the drag force is a lot. And as you see this graph, it's basically straight. So I guess it's safe to terminal velocity a lot faster. And that's it. Thank you and good night.